Hello there, Tim here. I'm doing an example from some very simple wave relationships in science of acoustics. That's the idea. So when we start talking about waves, we discuss the speed at which the waves travel and their frequency and wavelength. And usually the example I like to start with is one that's related to music a little bit. So the way I'm going to start talking about that, so I'll introduce my, my whiteboard here. Now, the wave speed equation is that the wave speed equals the frequency times the wavelength. And again, usually the frequency is written in hertz and the wavelength is written in meters or something like that. In symbols that equals, that's written V equals F times lambda. Lambda is a Greek symbol that's not so easy to type in directly into the whiteboard, but it looks like that that symbol is almost like an upside down Y. Anyway, that's the mathematical relationship, and the problem I want to do is figure out the wavelength of a common sound. Now, I figured a nice one to start with musically is middle C. So, right, middle C is one line below the staff in the treble clef and one line above the staff in the bass clef. And it's around the middle key of a piano or so, and the frequency of middle C is about 262 hertz. Now, one thing we'll discuss later as as a topic is the speed of sound in air depends on the temperature of the air, right? But at 20 degrees Celsius, it's 343 meters per second. It's very common for you to hear, or at least I'm told in audio classes, that 344 meters per second is the right number for room temperature. And that's also correct. I would say that 20 degrees Celsius is a little chillier than your average room temp at 68 Fahrenheit, which, certainly you could get by in, but often rooms are kept a little bit hotter than that. And so, I'll accept either one when I say room temperature, but if I specify that it's 20 degrees Celsius temperature, the speed of sound is 343 meters per second in air. In other media, again, this is a lesson for another time, in other media like liquids, solids, things like that, the number can be different. So the speed of sound is 343 meters per second. The frequency is 262 hertz. So what does that mean? Well, the question I'm going to find, or the question I'm going to answer, is what's the wavelength of middle C, and then I'll show how this might address how this might affect some musical issues. So if I start with that top equation, if I want to get the wavelength by itself, I divide both sides by F. So I go V over F equals F frequency times wavelength over F, and on the right side the F's divide out. So wave speed divided by frequency equals wavelength. Right, simple enough. So what I want to do is divide 343 meters per second divided by 262 hertz. Now, it's fine. What we see here is mathematically, just using these in red so I can cancel out. Hertz is the same as inverse seconds or cycles per second. So the meters per second and cycles per second are effectively, they're the same unit and they divide out. And all that's left is we have two numbers which we're going to divide, and we have meters. And meters, that's the correct unit for wavelength. So that's a good hint that I'm doing something right. Okay. Now, when I get to a point like this, I just reach for a calculator. I might as well show you my Google doing it. So what I had to do is divide 343 by 262, and I get an answer of about 1.31 if I round. Okay. So 1.31 is the answer. Going back to my board. Okay. What we get, right, This is the wavelength. It's 1.31 meters. And all right, a meter is longer than, by a little bit longer than a typical human's arm. Goes from the end of my fingers to about here if I measure it on myself. And that distance will be a little bit longer than 4 feet, just for reference. Now, how can I stretch this example a little bit to talk about music? Well, one of the, I mean, I'm mainly a guitar player, but one of the instruments I played, because my mom played and I needed to pick like a non-stringed band instrument to do band, as I played flute for a little while. Still have one, can't play it very well, but one thing I can relate this problem to, as far as music goes, is I've called up a hyperphysics page about the flute here, and the first thing it says is the flute is made in the form of an open air column about 66 centimeters long. Now, 66 centimeters long is a little bit longer than 2 feet. What's the significance of this, though? All right. Another place I looked up flute facts, right? 66 centimeters is about 26 inches. It's actually not so different from a typical guitar scale length, right? But the flute, right? This is the flute length, and it's about 66 centimeters. Now, if I double that, I just multiply that by 2, I get 132 centimeters, which you'll recall I got 131 centimeters for the wavelength of middle C. Now, that's no coincidence that the answers are very close to each other. You notice also in my Googling, I confirmed what the frequency of middle C was, and I was looking up all sorts of facts about the flute. Middle C is the lowest note that a flute can play. The way that you make it is basically you're pressing down on all of the keys at once, except for one of the pinkies, which I think is an opener, I believe. But essentially what you're doing is, right, the flute has keys, and the keys can cover holes. And when you press down over all of the holes, and you play in the lowest register possible, you get the middle C. And one thing that we'll discover a little bit later is that right, that for a tube that is open on 2 ends, the fundamental frequency that it plays, the wavelength is exactly double the length of the tube. So the flute is essentially a 66 centimeter tube. So if you double that length, you get 132 centimeters. And when played around room temperature, that will give you a frequency of middle C. Now, of course, this is adjustable when you there are a couple of ways you can adjust the tuning or intonation of the flute. You can roll in, roll out. It gives you a little bit of control. Also, the head joint can be moved in or out. And I recalled having to do that before, especially because when I was in marching band, part of the condition was we were outside in the Midwest in the cold. All right. So, a follow-up question I can ask is something like this. If it's cold outside, I wonder if I can just make this not red anymore. Yeah. If it's cold outside, how does the instrument's pitch change? So does it basically make the instrument go flat, or does it go sharp? All right, and that will determine how you have to adjust it physically to make sure you play in tune. So I thought I had a memory of the direction that went, but how do we figure it out? Well, the flute is the length that it is, about 66 centimeters. Specifically, we want to make it so normally it plays with a wavelength of 1.31 meters. So let's say the wavelength is still that. But what changes? It turns out at 0 degrees C, the speed of sound is 331 meters per second. So in a couple of weeks, we'll do some math and some examples showing the exact formula, which gives you the speed of sound at any temperature you want. But for right now, the speed of sound, just know that at 20 degrees Celsius, it's 343. At 0 degrees Celsius, the speed of sound is less. So what's the consequence of that? Well, frequency is speed divided by wavelength. That. So what is that? 331 meters per second. The wavelength is 1.31 meters. So what I've done is determine the numbers that I need to divide. I'm going to go back to my calculator and try 331 over 1.31. And you get 253 hertz. You get 253, okay? So I'm going to go back to my whiteboard here, share, and okay, 253 hertz. That's the answer here. So there are two parts to this question. First, under normal room temperature, I figured out what wavelength do you need to produce that. And it turns out that wavelength you get, it's about 4 feet long, but it's also about twice the length of a flute. Now, if you keep that instrument length the same and you change the speed of sound by going out in the cold, that same wavelength produced by that same instrument body will give you a frequency of 253 hertz, which is audibly lower. So the instrument goes flat. I will spend the last second here mentioning, I've asked classes before, which way do you think it goes? It goes flat or sharp? Many people remember that flat is the way that instruments often go in the cold, especially woodwinds like this. A good point that somebody made once, though, is that doesn't metal contract when it gets cold? So metal can expand when it heats up and it contracts when it gets cold. And shouldn't that affect the size and the wavelength of the waves produced? My answer to that is yes, but still you go flat. And the reason is the effect of getting cold changes the speed of sound more than it changes the length of the instrument. We see that the speed of sound dropped by something like 3 or 4%, and dropping a few degrees might cause some contraction, but it doesn't cause a contraction that's as big. So while your wavelength might be affected a little bit, it's a smaller effect. And so that it's not enough to make it go sharp instead of flat. It's not enough to wash out the effect of the speed of sound going down. So we'll do more on the speed of sound later, but I just wanted to do that musical example using the wave speed equation. And you should, by the time you're out of this class, and if not this class, then maybe your audio classes if you're taking them, you should be very familiar with the wave speed equals frequency times wavelength, and a couple of different ways of rearranging it. You can solve for wavelength or you can solve for frequency. So all of those should be possible. The same wave speed equation also works for light, and some homework you'll be doing. Maybe I'll do an example of that too in another video.